Hi, my name is Elizabeth Lang, and today I am going to walk you through a fascinating chiral molecule you've probably heard of, which is lactic acid. Starting off with the IUPAC name for the molecule, which is 2-hydroxypropanoic acid, with the common name being lactic acid. Lactic acid contains three key functional groups, a carboxylic acid group, a hydroxyl, and a methyl group. These groups give the molecule its polarity, acidity, and hydrogen bonding ability. When exploring properties of lactic acid, we can first look at the polarity. Lactic acid is a polar molecule, and this is due to the presence of the electronegative atoms, which are the oxygen in the hydroxyl and the carboxylic acid group, which create the dipole moments. Additionally, lactic acid is a weak organic acid, and the carboxylic acid group can donate a proton. The pKa of lactic acid is approximately 3.86, which means it's stronger than alcohols but weaker than mineral acids. Now, finally, lactic acid can both donate and accept hydrogen bonds due to the hydroxyl and carboxylic groups. These properties result in intermolecular hydrogen bonding, allowing it to dissolve in water. When taking a look at the chiral center and stereochemistry, we can prioritize the four different groups using Kahn-Ingold Prelog rules, which are hydroxyl group, carboxylic, methyl, and hydrogen. From that perspective, the rotation can be determined as counterclockwise, making it an S enantiomer of a lactic acid, which is non-superimposable. Lactic acid has one enantiomer. R, lactic acid, which is a mirror image but not superimposable, and there are no diastereomers since it only has one chiral center, and a constitutional isomer. Hydroxypropanoic acid can have the OH in another position, so it would be 3-hydroxypropanoic acid. Now, when we look at the structure details, carbon 1 and 2 are bonded to four different atoms/groups with no pi bonds, and that indicates an sp3 hybridization and a tetrahedral with shape with 109.5 degrees. Carbon 3 is double bonded to oxygen and is single bonded to an OH group, indicating three sigma bonds and a pi bond, leaving it at a sp2 hybridized with bond angles 120 degrees and a geometric shape as trigonal planar. Now, where exactly do we see lactic acid and its applications? Lactic acid is used in medicine as part of IV fluids. It is used also in biology during anaerobic respiration and in food as a preservative, as well as in the industry to produce a compostable plastic. Now, lactic acid is a simple yet powerful example of a chiral molecule found in nature, medicine, and the industry. So by understanding its stereochemistry and chemical properties, we gain a lot of insight into how small molecular changes can impact function and application in the real world context. And here are my references. Thank you.